All right, let's go. Number 12. The missing neutrinos. Ray Davis was not hunting cosmic secrets. In 1968, he was doing an accounting problem. He filled a 615-ton tank with perchloroethylene, ordinary dry cleaning fluid, buried it a mile underground in the Homestake gold mine in South Dakota, and set about counting the neutrinos streaming through it from the sun. Occasionally, a neutrino would convert a chlorine atom to argon. Davis's job was to count the argon. Standard solar physics, as calculated by John Bacall at the Institute for Advanced Study, was specific. The sun's proton-proton fusion chain produces a predictable neutrino flux, and Bacall spent years refining that prediction. The number he arrived at was roughly 7. 5 SNU, solar neutrino units, striking Davis's tank. Every physicist who checked the math converged on similar figures. It was one of the most confidently predicted numbers in astrophysics. Davis counted for years. He kept getting roughly 1/3 of Bacall's number. Year after year, a deficit so consistent it could not be dismissed as noise. 2 out of every 3 neutrinos the sun should have been producing were simply not there. Davis's Homestake experiment, in results published through the 1970s and updated over the following decades, converged on about 2.56 SNU against a predicted flux near 7.5. Bacall at EOS defended the theory. Davis at Brookhaven defended the apparatus. The community named it the solar neutrino problem, and it persisted through 30 years of parallel experiments. Kamiokande in Japan, SAGE in the Soviet Union, Galax under the Italian Alps, all finding the same shortfall in different ways. Was Davis's tank contaminated? Kamiokande's water Cherenkov detector, running from 1987 with completely different physics, found the same deficit. Was Bacall's math wrong? Every independent recomputation confirmed it. Was the solar core cooler than believed, quietly underproducing energy? Helioseismology ruled that out. The interior temperature was probed through sound waves and matched the model. Was something inside the sun absorbing the neutrinos? Nothing in the standard model of particle physics permitted that. For 30 years, no explanation fit. The answer arrived in 2001 from the Sudbury Neutrino Observatory in Ontario. The missing 2/3 were still there. They had simply changed flavor on the 8-minute trip from the core. Takaaki Kajita and Arthur MacDonald received the 2015 Nobel Prize for confirming this, which forced a rewrite of particle physics. Neutrinos have mass, and the standard model as written has no mechanism to give them any. You have been swimming in an ocean of particles whose most basic property physics could not describe for 3 decades, and the current answer only opened a bigger question, where mass itself comes from. The missing particles were the easy mystery. Number 11. The corona is 200 times hotter than the surface. In the 1940s, the Swedish spectroscopist Bengt Edeln was doing catalog work, identifying strange emission lines observed in the solar corona during eclipses. These lines had defied identification for decades and were briefly attributed to a hypothetical new element called coronium. Edeln was closing what looked like a nagging spectroscopic loose end. The prediction from thermodynamics is one of the most basic in physics. Heat flows from hot to cold. The sun's energy is generated in the core at roughly 15 million degrees Celsius, radiates outward, and by the time it reaches the photosphere, the visible surface, it is cooled to about 5,500 C. Above the surface, the tenuous outer atmosphere should be cooler still. Edeln identified the mystery lines as coming from iron atoms stripped of 13 electrons. To do that requires temperatures on the order of 1,000,000 degrees. The corona, which sits directly above the 5,500 C photosphere, was subsequently confirmed at temperatures between 1 and 3 million degrees. Edeln published the ionized iron identification in 1943 in Zeitschrift for Astrophysics. The temperature gradient inverts as you move away from the heat source. The atmosphere is roughly 200 times hotter than the star beneath it. Was there a hidden heat source? There is not. The corona is heated by energy transferred from the surface. Are nanoflares, countless small magnetic reconnection events proposed by Eugene Parker at the University of Chicago in his 1988 paper in the Astrophysical Journal, supplying the energy? Parker's solar probe, launched in 2018 and now diving closer to the Sun than any spacecraft in history, has found suggestive evidence but no definitive confirmation. Are Alphean waves, magneto-hydrodynamic waves along field lines, carrying the energy up and dumping it in the corona? Parker's solar probe has detected them, but the accounting of how much energy they deposit remains contested. Both mechanisms may contribute. Neither has been shown to be sufficient. This is not a resolved textbook problem. It is a live open problem being actively investigated by a spacecraft that, as you watch this, is orbiting inside the corona itself. The Sun's atmosphere is defying the same thermodynamic rule that governs the coffee cooling on your desk, and it is doing it by 2 orders of magnitude. Every star we look at exhibits some version of coronal heating, which means the mechanism, whatever it is not a quirk of our Sun. It is a rule of stars we have not written down yet. Sunlight itself refuses to be as young as it looks. Number 10. Light takes 100,000 years to escape. Arthur Eddington was working on the internal structure of stars in the 1920s, not on a mystery, on infrastructure. His job was to model how energy generated in the core could reach the surface. He was assembling the first coherent theory of stellar interiors, published as The Internal Constitution of the Stars through Cambridge in 1926. This was foundational astrophysics, laying the groundwork for everything that came after. The naive prediction, light created in the core travels outward at 299, 792 kilometers per second, covers the roughly 696,000 kilometer radius of the Sun, and emerges in about 2.3 seconds. Photons are fast. The Sun is not that big. The arithmetic is trivial. The arithmetic is also wrong. The interior of the Sun is a plasma so dense that a photon cannot travel more than a fraction of a centimeter before scattering off an electron. Direction randomized. Repeat, modern calculations based on stellar structure models place the mean free path of a photon in the deep solar interior at around 1 millimeter. The number of scattering events required to random walk from the core to the surface is astronomical. Estimates for the total time range from around 10,000 years at the low end to roughly 170,000 years at the high end, depending on model assumptions. A commonly cited figure is on the order of 100,000 years. Could the photon take a straighter path? Statistical mechanics forbids it, and interior opacity is measured, not assumed. Could photons be created near the surface instead of the core? A trivial fraction are, the overwhelming majority of solar luminosity originates in the core. Could the mean free path be much longer than believed? Helioseismic measurements of interior density leave no room for that. Could the total time be a factor of 10 off? Perhaps it would still be many thousands of years, which means the sunlight warming your face right now was not created 8 minutes ago. It was created in the Sun's core when anatomically modern humans were still sharing this planet with Neanderthals. The photon that entered your retina to let you see this screen has been walking outward from the Sun's center for longer than every human civilization combined, multiplied by 20. The Sun you see is not the Sun as it is. It is the Sun as it was, in ways that go past the standard 8-minute delay. Every sunrise is a delivery from prehistory. If the Sun's fusion stopped this instant, you would not know. Not for millennia. That same opaque interior hides a rotation nobody expected. Number 9. The core spins faster than the surface. In the mid-2000s, a team led by Raphael Garca at the Commissariat L'Énergie Atomique in Saclay, France, was doing routine helioseismic analysis. They were combing through years of data from the Golf instrument aboard the SOHO spacecraft, an ESA-NASA solar observatory that had been staring at the Sun since 1995. The goal was to detect solar gravity modes, or G modes, whose signatures had been hunted since the 1970s. The prevailing picture of solar rotation was already strange. The surface rotates differentially, about 25 days at the equator, 35 days at the poles. Helioseismology through the 1990s had shown the interior rotates like a rigid body down to the base of the convection zone. Below that, the assumption was that the core rotated at roughly the same rate as the radiative zone above it. Garca's team reported something different. The core appeared to be rotating several times faster than the surface layers. The paper appeared in Science in 2007, Tracking Solar Gravity Modes, the Dynamics of the Solar Core, by Rafael Garca and colleagues. The result was based on statistical detection of low-frequency oscillation patterns in about a decade of golf data. Subsequent work by Eric Fossat and colleagues in 2017 in Astronomy and Astrophysics, using different techniques, reported similar conclusions. A core rotating with a period on the order of a week. Is the detection real? Some independent analyses have failed to reproduce the G-mode signal, and the community remains divided. Is there a physical mechanism that could sustain such a shear? A rapidly spinning young sun that spun down at the surface but preserved core angular momentum is the leading candidate. But existing angular momentum transport theories predict the interior should have spun down along with the surface over 4.6 billion years. Could magnetic braking have been asymmetric? No self-consistent model reproduces the observed shear cleanly. Could the observed signal be an artifact? Possibly, and this is precisely why the result remains contested nearly 2 decades later. If the detection is right, the Sun is effectively two objects, an inner rotor turning several times faster than the outer star that contains it. And that shear is where magnetic fields are amplified, which means the space weather that periodically fries your GPs may originate in a hidden rotation we still cannot confirm. We do not know how fast the center of our star turns. That question has been open for nearly 18 years, and the reason we can even ask is that the Sun rings. Number 8. We can hear inside it. In 1960, Robert Layton, Robert Noyes, and George Simon at Caltech were making high-resolution measurements of the Sun's surface. They were not looking for anything dramatic. They were mapping small-scale motions in the photosphere as part of a general survey. Doppler shifts, up and down movement of gas, the kind of measurement that fills a graduate student's afternoon. The expectation was that the surface would show turbulent granulation, chaotic bubbling driven by convection underneath. That is what it looks like at first glance. Small cells appear, evolve, dissolve, effectively random. Layton's team found the surface was oscillating in synchrony, patches of gas everywhere on the disk bobbing up and down with a shared 5-minute rhythm. The result appeared in the Astrophysical Journal in 1962, Velocity Fields in the Solar Atmosphere. Preliminary Report, by Layton, Noyes, and Simon. For a decade, the oscillations were interpreted as local surface phenomena. Then, in 1970 and 1971, Roger Ulrich at UCLA, along with John Liebacher and Robert Stein, working independently, proposed that the oscillations were global, standing sound waves resonating throughout the entire solar interior. The field of helioseismology was born. Could the oscillations be surface turbulence after all? The coherence across the entire disk ruled that out. Could they be a mathematical artifact of the analysis? Instruments across 3 continents confirmed them. Were they too weak to probe the deep interior? The Gong network of 6 ground stations, established in the 1990s, and the MDI and HMI instruments aboard the SOHO and STU spacecraft. Resolved oscillations at millions of distinct modes, sensitive to structure at every depth. Every failed alternative sharpened the picture. The Sun was ringing across roughly 10 million distinct modes simultaneously, which means the interior of the Sun, its temperature profile, its rotation, its density at every layer, the boundary of the convection zone at about 71. 3% of the solar radius was mapped not by any telescope but by listening. The same principle by which seismologists map Earth's core from earthquakes was turned upside down and pointed at the Sun. We have already been inside the Sun, through sound, not sight. A star 900,000 miles across, and the way we know its heart is by decoding the note it hums at us across 93 million miles of vacuum. And the note is still being decoded. New modes are still being identified, but when the listening and the looking disagree, something has to give. Number 7. The abundance problem. In the early 2000s, Martin Asplund, then at the Australian National University, and colleagues Nicolas Greves and Jacques Sauval were doing what looked like a maintenance job: solar abundance measurements. The fractions of each element in the sun's photosphere are the reference standard for stellar astrophysics. The team was updating older values with three-dimensional, non-equilibrium radiative transfer models. Higher fidelity, better physics. A refinement, nothing more. The setup was straightforward. Solar composition, determined from spectroscopy, should agree with the composition inferred from helioseismology, which maps the interior by sound. Both methods had been in good agreement for decades. Everyone expected the new spectroscopy to nudge the numbers slightly and everyone to move on. The revised metallicity came in significantly lower, around 30 to 40% less carbon, nitrogen, and oxygen than the previous standard values. The results appeared in a series of papers, most influentially the Solar Chemical Composition by Asplund, Greves, and Sauval in Nuclear Physics A in 2005, and refined further in Annual Review of Astronomy and Astrophysics in 2009. The new abundances broke the agreement with helioseismology. Predicted sound speeds, the depth of the convection zone, the helium abundance in the envelope, all diverged from what the sun was audibly telling us. The problem persists 20 years later. Was the spectroscopy wrong? Independent groups using different radiative transfer codes have largely confirmed the lower abundances. Was helioseismology wrong? Its measurements are among the most precise in astrophysics. The sound speed profile is known to fractions of a percent. Was the opacity of the solar plasma miscalculated? Sandia National Laboratory's Z-machine, in results reported by Jim Bailey and colleagues in Nature in 2015, measured iron opacity at solar interior conditions and found values 30 to 400% higher than theoretical predictions, helpful, but not enough to close the gap. Are the fusion cross-sections off? No. Laboratory measurements are tight. Is the physics of convection modeled wrongly at the base of the convection zone? Possibly, but no proposed fix reproduces both spectroscopy and seismology cleanly, which means that at this moment, physicists cannot say with confidence what the sun is made of, and every star's composition in every catalog is calibrated against the sun. If our reference standard is wrong, every downstream number, every stellar age, every metallicity, every mass estimate inherits the error. The star closest to us, the star we understand better than any other, is a star whose chemistry we cannot pin down. One element on that periodic table points somewhere else entirely. Number 6. The sun has lost almost all its lithium. In the 1950s and 1960s, stellar astronomers were assembling a catalog of chemical abundances across many stars. Lithium was of particular interest because it is fragile, destroyed at temperatures above about 2.5 million Kelvin, which occurs at modest depths inside sun-like stars. Measuring lithium was routine spectroscopy on the way to bigger questions. The setup was clean. The primordial lithium abundance produced by Big Bang nucleosynthesis is known to within a factor of a few. Sun-like main sequence stars should have depleted some but retained most of it, unless something reached down and mixed the surface layers with the hot interior. The sun's photosphere contains only about 1% of its primordial lithium. Its closest stellar twins hold far more. The numbers are stark. Solar photospheric lithium is measured at roughly AW 1.05 on the standard logarithmic scale, against a meteoritic and presumably primordial for our sun value of about 3.3. Around 99% of the sun's original lithium is gone. In 2009, Garrick Israelian and colleagues at the Instituto de Astrofísica de Canarias published a paper in Nature titled Enhanced Lithium Depletion in Sun, like Stars with Orbiting Planets, reporting that stars hosting detected giant planets, including our sun, showed significantly stronger lithium depletion than stars without. Is the depletion just age? Older stars deplete more lithium, but the sun appears more depleted than expected for its age against comparable field stars. Is there enhanced mixing driven by rotation? Rotational mixing is a candidate, but modeling itself consistently for the sun has not fully explained the deficit. Could the initial abundance have been lower? There is no independent way to prove that. Does the correlation with exoplanets survive statistical scrutiny? Follow-up studies, including work by Michael Baumann and colleagues in astronomy and astrophysics in 2010, contested the strength of the correlation. Other groups have since defended it. The mechanism, if there is one, remains unidentified, which raises an uncomfortable possibility. Planet formation may leave a chemical signature on the host star's surface. If so, the chemistry of the sun encodes information about the birth of the Earth beneath your feet, information we do not yet know how to read. Something dragged the sun's lithium down and burned it. What did the dragging is unknown. Whether Earth is Y is unknown. The layer where the dragging must happen sits 4% of the way in. Number 5. The Tachocline. In the late 1980s, helioseismologists were doing what had become routine, mapping the interior rotation of the Sun using thousands of resolved oscillation modes. Douglas Goff at Cambridge, Jürgen Christensen Dalsgaard at Aarhus, and colleagues across several institutions were refining maps of angular velocity at every depth. Better data, better inversions, better resolution. Iterative work. The prediction, held for decades, was that the Sun's rotation profile transitioned smoothly from a differentially rotating convection zone to a rigidly rotating radiative interior. There ought to be a gradient, but a gentle one. Convection stirs the outer 30%. The deeper radiative zone below sits still, mixed only weakly. The transition should be spread out. It is not spread out. It is a knife edge, a thin sheer layer where rotation changes abruptly. Edward Spiegel at Columbia and Jean-Paul Zahn at the Observatoire de Meudon published the solar Tachocline in Astronomy and Astrophysics in 1992, naming and characterizing the layer. Later helioseismic work by Sasha Kosovachev, Michael Thompson, and others placed its center at approximately 0. 693 solar radii, with a thickness of only about 0.04 solar radii, roughly 4% of the Sun's radius. A boundary that thin around a star 1.4 million kilometers across. Is it stable? The thinness itself is unexplained. Some mechanism must be preventing it from spreading over billions of years. Is it a wave phenomenon? Goff and Michael McIntyre proposed in a 1998 Nature paper that a fossil magnetic field in the radiative interior could pin the Tachocline in place. Is it turbulent? Zahn and colleagues argued for anisotropic turbulence maintaining the shear. Neither picture is settled. And the layer is believed to be where the Sun's magnetic dynamo, the engine of the entire 11-year cycle, is generated, through the stretching of magnetic field lines in the shear. Which means all the magnetic weather in the solar system, every flare, every coronal mass ejection, every disruption to your GPS signal, originates in a seam thinner than a rounding error, a layer 4% thick around a star whose diameter is 109 times the diameter of Earth. We do not know what holds it there. We do not know what makes it so thin. We do not know exactly how it makes the field. The engine of the entire solar cycle is a boundary we can barely resolve, and that engine refuses to run on a predictable schedule. Number 4. The dynamo we cannot predict. In 1843, the German amateur astronomer Heinrich Schwabe was hunting for a planet inside the orbit of Mercury. To spot such a body against the solar disk, he needed a long baseline of daily sunspot drawings for reference. 17 years of tedious observing. He never found the planet. He did find something else. The pattern he stumbled onto was that sunspots do not appear at random. They wax and wane on a rhythm of approximately 11 years. This was so consistent across the following century that solar physicists began to treat cycle prediction as a solvable engineering problem, measure the state of the Sun near solar minimum, and forecast the amplitude of the next cycle. The predictions have been unreliable in ways nobody expected. Cycle 24, which peaked around 2014, was forecast by an official NASA NOAA panel in 2007 that split into two camps, a strong cycle near 140 sunspots or a weaker one near 90. The observed cycle came in weaker than most predictions, with a smooth peak around 16, the weakest solar maximum in roughly a century. The historical record is worse than the modeling. Between 1645 and 1715, an interval named the Maunder Minimum after Edward Maunder, who documented it in an 1890 paper in the monthly notices of the Royal Astronomical Society. Sunspot counts collapsed to near zero for 70 years. The 11-year cycle effectively stopped. Beryllium-10 isotopes and ice cores show reduced solar activity across that interval, and it coincided with the coldest phase of the Little Ice Age in Europe. Is the Dynamo a chaotic system? Somewhat. Nonlinear feedbacks in the magnetic field make long-term prediction fundamentally difficult. Are the physics models simply too coarse? Yes, but even the highest resolution magnetohydrodynamic simulations by teams at Howe and Boulder and MPs in Göttingen cannot reliably reproduce past cycles or forecast future ones with useful precision. Is there a hidden secondary cycle modulating amplitude? Possibly the Gleisberg cycle of roughly 87 years and the longer Seuss cycle of around 210 years. Appear in the record, but their physical basis is unclear. Can we tell whether we are heading into another minimum? Not with any confidence. Which matters because the strength of the solar cycle governs the density of the upper atmosphere, thickening it, dragging down satellites, and it drives the solar wind that reshapes Earth's magnetosphere. Every GPS fix, every long-distance power grid, every low Earth orbit satellite operates inside a weather system we cannot forecast. Something is stirring the dynamo we can hear but not read. One proposed reason we can't read it lies at the very center. Number 3. Dark matter may be trapped in the core. In 1985, Bill Press and David Spergel at Princeton were working through the consequences of dark matter for stellar interiors. The paper was theoretical infrastructure. If dark matter particles are what most of the universe is made of, they should occasionally scatter off nuclei inside stars, lose energy, and get captured. That capture rate, integrated over the age of the sun, is calculable. Press and Spergel were doing the calculation. The setup was the same standard solar model everyone works from. The sun sweeps through the Milky Way's dark matter halo at roughly 220 kilometers per second. If the particles have the properties of leading candidates, weakly interacting massive particles, or WIMPs, in the mass range of a few to a few hundred times the proton mass. Some fraction gets gravitationally bound. Over 4.6 billion years, that fraction accumulates in the core. Press and Spergel found the sun could plausibly hold a reservoir of dark matter, enough to alter how heat moves through the deep interior. Their paper, Capture by the Sun of a Galactic Population of Weakly Interacting Massive Particles, appeared in the Astrophysical Journal in 1985. The mechanism was extended over the following decades, by Andrew Gould in a series of APJ papers in the late 1980s, and more recently by researchers including Aaron Vincent and Pat Scott, whose work in Physical Review Letters and JCAP in the 2010s explored how dark matter with specific interaction properties could redistribute heat in the solar core and, remarkably, potentially ease part of the solar abundance problem. Have we seen direct evidence of dark matter in the sun? Not conclusively. IceCube at the South Pole and Super Kamiokande have searched for high-energy neutrinos produced by dark matter annihilating in the sun's core. Upper limits have tightened, but nothing definitive. Is the abundance problem fixed by dark matter clean? It requires a fairly narrow range of dark matter properties, asymmetric or velocity-dependent scattering, that is neither ruled out nor confirmed. Could the effect be mimicked by conventional physics? Possibly, but no conventional fix works cleanly either, which means one of the two great mysteries of astrophysics, what the universe is mostly made of. And why our nearest star doesn't quite fit our model may be the same mystery, and its answer may be sitting at the center of the sun right now. The sun may already contain, in its core, a sample of the substance that makes up roughly 27% of the universe, and we cannot reach in and check. And while we can't reach in, something inside can still reach out. Number 2. A Carrington-level flare is overdue. On September 1st, 1859, the English astronomer Richard Carrington was doing routine sunspot mapping at his private observatory in Red Hill, Surrey. He had a solar image projected onto a screen and was sketching the positions of spots, a daily task he had performed for years. That morning, he saw 2 patches of intensely bright white light appear inside a sunspot group and then fade over roughly 5 minutes. He assumed his optics were failing. The setup he could not have known was that the sun had launched a coronal mass ejection, a huge magnetized plasma bubble, directly at Earth. Standard space weather physics, worked out much later, says such an event ionizes the upper atmosphere, induces enormous currents in long conductors on the ground, and lights up aurorae far outside the polar zones. Roughly 17 hours after Carrington's flash, the CME arrived. Telegraph systems across Europe and North America failed. Some sparked and caught fire. Operators reported being able to send messages without batteries connected. The induced current alone was enough. The 1859 event, later reconstructed by Bruce Tsuritani at JPL and others in a 2003 paper in the Journal of Geophysical Research, produced aurorae visible as far south as the Caribbean and Colombia. Records were cataloged by Balfour Stewart at Kew Observatory in the days after. In July 2012, NASA's StereoA spacecraft recorded a coronal mass ejection of comparable magnitude that crossed Earth's orbit, but Earth was not there. It passed through the location where our planet had been about 9 days earlier. Dan Baker at the University of Colorado and colleagues analyzed the event and concluded its Earth-directed impact would have been Carrington class. Was the 2012 event a fluke? Modeling by Pete Riley at Predictive Science in a 2012 space weather paper estimated the probability of a Carrington class event striking Earth in any given decade at roughly 12%. Are modern grids more robust than 1859 telegraph lines? Not really. The same physics applies on a vastly larger and more interconnected infrastructure. Are transformer replacements readily available? Global spare capacity for large, high-voltage transformers is limited. Production lead times run months to years. Can we forecast the trajectory in advance? We have between 15 and 30 hours warning at best from the moment a CME leaves the sun, which means a routine, historically precedented event would collapse power grids on continental scales. Weeks to years without electricity in some regions. Ordinary industrial civilization is protected by the geometry of the sun's aim. The 2012 CME did not miss because we were lucky about where it went. It missed because we were lucky about when. Eventually the sun hits with something we cannot survive at all. Number 1. The sun will erase the evidence. In the late 2000s, K.P. Schurter at the University of Guanajuato and Robert Smith at the University of Sussex were doing the equivalent of an actuarial calculation for a star. They combined modern stellar evolution codes with updated models of mass loss and orbital dynamics. The question was straightforward. What is the future history of the sun and the planets around it? Bookkeeping, not prophecy. The setup was the standard picture. The sun is roughly 4.6 billion years old and about halfway through its main sequence lifetime. As hydrogen in the core is exhausted, the core contracts, the outer envelope expands, and the luminosity climbs. Long before helium ignition, the surface temperature of Earth crosses lines that biology cannot survive. Earth does not need to be swallowed to become uninhabitable. Shorter and Smith reported that Earth's surface will be sterilized well before the sun becomes a red giant. Their paper, Distant Future of the Sun and Earth Revisited, appeared in the monthly notices of the Royal Astronomical Society in 2008. Solar luminosity has risen by roughly 30% since the sun formed and will keep rising. Their models suggest oceans boil off in something like 1 to 2 billion years. Even accounting for solar mass loss expanding Earth's orbit outward, Earth is likely to be engulfed during the red giant phase, in roughly 7.6 billion years. Long before that, the surface will be molten. Every rock formation, every fossil bed, every ice core, every buried city, flattened, melted, and eventually ionized. Can we escape the timeline by moving Earth outward through gravitational assists? Don Korakansky, Gregory Laughlin, and Fred Adams proposed exactly this in Astrophysics and Space Science in 2001, using repeated close passes of a large asteroid to nudge Earth's orbit outward gradually. The engineering is beyond current civilization. Can we simply move to another star? Interstellar travel at any meaningful scale is not on the horizon. Can we preserve records off-world within the solar system? Every archive we place is subject to the same expanding star. Can anything we send beyond it survive? Perhaps Voyager 1 and 2 will drift onward for billions of years, but their engraved plaques will be etched into meaningless powder by micrometeoroid erosion long before any civilization could recover them. Which means every trace of what happened on this planet, every photograph, every book, every genome sequenced, every question ever asked about the sun in a video like this one is on a clock. Not a metaphorical one, a stellar one. The whole video was about what the sun is hiding. The last answer is the thing the sun will hide. Us, every entry on this list, sits at the center of theories we have tested more carefully than almost anything else in science. The neutrinos, the corona, the interior we can only hear, the composition we cannot pin down, the flare we cannot forecast, the ending we cannot outrun. The universe is not confused. Our best tested pictures of it are the ones with the deepest holes. The sun is 8 minutes away, and we still do not know what it is. And we are running out of time to find out. If you want to see more videos like this, click the video on screen now.